Hello, and welcome to the October webinar from the IEA Clean Coal Centre. My name is Deborah Adams, and I'm Communications Manager here. Our monthly webinars are based on our technical reports, which are available from our website, www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after one-off registration. Please visit our website for details. Today's webinar is presented by Nicol on the direct injection carbon engine. His report on the subject is out in draft at the moment and will be published and available on our website by the end of the year. If you have any questions during the talk, please use the Ask a Question box at the top of your screen. If you add your email address as well, Kyle can send you a fuller answer if we run out of time. Okay, Kyle, over to you.
Thank you, Debo. My name is Nicol, and I will now present my recent work. Imagine yourself going to the petrol station to fill your car up with coal. This could be possible with coal-fueled diesel engines. The aim of this webinar is to show you how coal can be used to fuel coal-fueled diesel engines as part of an advanced power generation supply. Rudolf Diesel first trialled firing coal dusts in internal combustion engines 122 years ago. He then found that petroleum fuels were easier to burn and a diesel engine was born. However, coal dusts were further developed in Germany and then used in Germany and Japan at the end of the Second World War due to fuel shortages. Engine lifetimes were up to 12,000 hours and the efficiencies were up to 30%, which was twice that of steam power at the time. However, coal dust engines have two main problems. Firstly, the coal dust and the ash get stuck in the engine oil, which causes excessive wear on the engine components. And also, coal dust is like gunpowder. It is explosive and difficult to handle. In the 1960s, laboratory research in the USA and Switzerland discovered that firing coal dust in a water slurry, split roughly 50-50, directly into an engine is more effective than coal dust firing. Coal water fuels have higher combustion efficiencies, they cause less wear, the water has a small effect on thermal efficiency, the slurries are not explosive, and also having the coal in a water slurry provides an excellent opportunity to wash out the minerals, which reduces wear and also reduces emissions. The minerals can be washed or beneficiated using physical and chemical beneficiation methods. At the time, physical washing could produce coal water fuels with 2 to 3% ash, and the chemical beneficiation could produce coal water fuels with less than 0.5% of ash. But the chemical beneficiation methods are generally more expensive. With all coal water fuels, additives can be used to control viscosity and stability. To further minimise wear, an adapted diesel engine was developed that uses harder engine materials and a purpose-built fuel injector. The oil crisis in the 1970s prompted the Department of Energy in the USA to fund a comprehensive coal-fueled diesel engine research and development program from 1978 to 2004, which had the following highlights. In the 1980s, a mine haul truck was fitted with a Detroit diesel engine. This was driven on coal water fuel at engine speeds up to 1900 RPM, which equates to 32 injections of fuel per second. GE and GM both investigated, General Motors and General Electric both investigated DICE for train locomotives. GM tested firing chemically beneficiated coal water fuel in a standard diesel engine locomotive. This was to avoid a complete redesign of their engine. But the chemically beneficiated coal was much more expensive than diesel, and this engine was economically inviable. GE fired a cheaper, physically beneficiated coal water fuel in an adapted diesel engine. This method worked and had lower projected costs than diesel-fueled diesel engines at the time, and this progressed to full-scale demonstration, as shown in the picture here. But the problem with this was integrating an emission control system and subsequent control with an adapted diesel engine onto one train locomotive. In 1993, Cooper Bessemer operated a large-scale diesel engine, combined heat and power plant on physically beneficiated coal water fuel with an emission control system. As this was the most successful demonstration, the US Department of Energy provided some funding for long-term operation, but low gas prices and funding issues led to the cancellation of the program in 2006. More recently, higher oil and gas prices, tougher environmental and energy security drivers, coupled with advances in coal processing and diesel engine technology, such as electronic control and larger cylinders, favour the commercialisation of coal-fuelled diesel engines. The high flexibility and black start capability and the high efficiency at all loads allow maximum utilisation of intermittent renewable energy whilst keeping emissions from itself low, so coal-fuelled diesel engines would be ideal for power generation. Since 2008, the Commonwealth Scientific and Industrial Research Organisation, or CSIRO, in Australia have been investigating the subject. Economic analysis conducted by CSIRO, ANLEC R&D and MAN show that there are favourable economics in power generation applications, such as used against diesel fuel in distributed generation or when used against gas in centralised generation. This graph shows the estimated thermal efficiency of coal-fuelled diesel engines compared to that of gas, pulverised coal and coal gasification power plant. As opposed to firing coal water fuel, CSIRO have developed the cleaner micronized refined carbons using state-of-the-art physical beneficiation methods. MRC, using physical or chemical beneficiation methods, is now produced on pilot scale by a few companies. Glencore Extrata are producing physically beneficiated MRC using froth flotation, which contains roughly 2% mineral matter. Chemical beneficiation methods, which can reduce the mineral content in MRC to less than 0.2%, have been developed by Nicol, Intertek, Kia, AMAX and Kobe. The adapted diesel engine is known as the direct injection carbon engine, or DICE, which is based on technology developed by the US Department of Energy's coal-fuelled diesel engine research and development program, as explained previously. Diesel engines on container ships now have 55% electrical efficiency, and they are more tolerant to lower quality fuels due to larger clearances. Such engines could be used as a template for DICE. DICE can run on heavy fuel oil, diesel fuel and gas, so that the lowest cost fuel can be used at any time. To create a single centralised power plant, multiple engines can be combined, which introduces economies of modularity as opposed to economies of scale. DICE is tolerant to high temperature, high altitude and low water environments, which therefore could provide a low-cost power generation option for parts of Africa and Asia. MRC does not limit itself to black coal. It can use coal tailings, brown coal and biomass as a feedstock, hence the use of the word carbon as opposed to coal in the acronyms MRC and DICE. However, brown coal and biomass have a high moisture content and low energy density. This has two drawbacks. It is expensive to transport low energy density fuel, and more fuel has to be injected into the engine to achieve a practical power output. This means that more injectors or lower speed engines are required. To avoid these drawbacks, high moisture fuel can be upgraded using hydrothermal dewatering, which essentially accelerates the qualification process, removing at least half of the moisture content. JGC are operating a demonstration hydrothermal dewatering plant in Indonesia and plan to operate a commercial plant in 2018. Process flow diagrams and photos are shown below. Ignite Energy Resources and Exogen in Australia are operating pilot scale tests. RWE Power in Germany have developed a different approach to brown coals. To compete with natural gas peaking power plant, DICE can be located near to a brown coal mine and use the coal water fuel that has not been washed or upgraded. The drawback to this approach is that engine lifetime is compromised, but by how much is unknown. CSIRO tested MRC in a spray chamber to evaluate the atomization and combustion characteristics of MRC, both of which are excellent. CSIRO's laboratory DICE, which has run successfully on MRC. No fouling has been detected and the engine has low NOx emissions. In wear tests, low rank coal MRC has detected no wear. For high rank coal MRC, a small amount of wear has been detected when using hardened steels, and no wear has been detected when using tungsten carbide coated steels. This figure lists the components in MRC and DICE. Items highlighted in green are commercially available, and items highlighted in yellow have been proven on a pilot scale. So, roughly speaking, according to this diagram, around 40% of the components in MRC DICE are already commercially available. MAN, Diesel and Turbo are now operating a 1 megawatt pilot scale DICE in Japan on MRC produced by multiple companies. The next milestone with this pilot scale test is results due in 2016. Assuming acceptable results from DICE and the MRC fuel cycle, then DICE could proceed to the next stage of development. Long-term, large-scale demonstration of DICE will give accurate measures of performance, such as wear rates, component lifetime, efficiency, flexibility and availability. But this will require around 160 million Australian dollars of venture capital. The MRC fuel cycle, which includes coal beneficiation and hydrothermal treatment, also has to be demonstrated at large scale to provide details on the best quality MRC that can be produced. This Gantt chart shows the previous research and development programs split into generations. Sorry, it's not interplanetary generations. Despite numerous successful tests, previous attempts to commercialise coal-fueled diesel engines have failed, largely due to persistently low oil and gas prices. As some final remarks, coal-fueled diesel engines are not a new idea. The concept of firing a washed coal in a water slurry in an adapted diesel engine has been technically proven in the USA on pilot scale and in short-term large-scale tests. Large-scale demonstration of both DICE technology and MRC fuel cycle are required before such technology can be commercialised. Thank you for listening, and I would like to take any questions.
Thanks very much, Carl, for an interesting presentation. We're now just going to see if any questions have come in. Okay, Carl, we've got the first one here. How much testing do you think is required for large-scale demonstration?
At the moment, it is thought that around 8,000 hours of testing is needed to get an accurate measure of performance.
Thank you. And in particular, why are they testing DICE in Japan?
This is simply because MAN Diesel and Turbo already have an engine testing facility in Japan.
Okay, and the third question has come in. Kyle, what state does the coal dust need to be in for it to become explosive?
It simply needs to be dry and micronized to a fine enough degree. The explosivity limits depend on the heat, the amount of oxygen available. But generally, if you grind coal, especially brown coal, it is explosive.
Are there any plans to use DICE to power cars or container ships, do you know?
Cars use high-speed engines. These operate up to 80,000 revs per minute or even higher. The MRC would have to have a low level of ash to allow a practical engine lifetime. This probably isn't economically viable with current petrol and diesel prices. With container ships, there's been some interest by the large companies who operate container ships in DICE, but there's two important points here. Firstly, the container ship market is a few percent that of the power generation market, and also the engine manufacturers already have their engines in container ships, so there's not much incentive to develop a new DICE engine.
Okay, Kyle, do you have an opinion on what is the best fuel tested so far for DICE? I'm not quite sure what they mean by best. I guess economics and other factors.
The best fuel tested for DICE, I think we'd have to wait for results from pilot scale testing in 2016. If you read the report, you can get more of an idea of what type of, of what the specifications are required, but further examination is required on different coals and of the economics of the MRC process at the time.
Thank you. There's quite a few questions coming in. What sort of transportation options would there be for MRC to be supplied worldwide?
MRC is very similar to oil. It can largely use the same infrastructure. Long-term storage will need agitated or stirred tanks. Another option is to transport a paste MRC and then dilute it further with water at the point of use.
Do you think government funding is likely to be available for DICE in the near future?
Yes.
That's interesting. Do you mean for research or actually for using it?
to fund the pilot scale testing now, and hopefully to fund the large scale testing, which is not decided where that'll be, but hopefully it'll be available for large scale testing from 2016 onwards.
Okay, and then this is the last question at the moment. Kyle, could you give us some data about experience in measuring gas emissions and also about fouling inside the chamber?
So far, no tests have detected fouling. However, long-term testing is required to answer that question, of which 8,000 hours or more testing is needed. So I can't answer the question about fouling definitely. The emissions, generally speaking, that there's low NOx emissions. There's very good combustion efficiency, so there's low hydrocarbon and CO emissions. There should be low CO2 emissions with the high efficiency. With sulfur, so the sulfur can be washed out in the beneficiation stage, or if not, for a DICE power plant, there can be conventional desulfurization technologies such as wet scrubbing. What other emissions? As most of the minerals are washed out in the beneficiation stage, the emissions should be relatively low. Oh, and then any particulate emissions can be caught out using a cyclone, if not a fabric filter or an ESP. And these technologies, especially the ESP and fabric filter, scrub over and catch over 99.8% of particulate emissions.
Okay, Kyle, one more question has come in. Do you think DICE could be a game changer for coal generation?
If enough venture capital is put into large-scale demonstration and there are committed resources of engineering firms, then yes, I do think that DICE can be a game changer for coal power generation. As I said, it fits in well with energy grids, with large amounts of intermittent renewables, but it also works well as baseload. The question is when it will become a game changer.
Thanks very much, Carl. It's obviously provoking quite a lot of discussion. Let me just remind you that if you want more information on this subject, Carl's PowerPoint will be available to download from the webinar page of our website later on today, and his report will be published in the next couple of months, I'm sure. No more questions have come in, so I'm just going to remind you that our next webinar, the November webinar, will take place on Wednesday the 19th, when our colleague Chen Zhu will be presenting the subject of her latest research, which is high efficiency power generation, a review of alternative system concepts. So I hope you'll listen in then. If you've got any more questions for Kyle, send him an email. Thanks for listening. Bye-bye.